So, welcome everybody to the first ever joint session of MFPS and ACT. On behalf of the 4 PC chairs of the 2 conferences, I'm Michael Johnston and I'm chairing the session. I think most of you already know Andy Pitts and his work, but still I have to say a few things. So Andy was doing seminal work in the applications of category theory before the term applied category theory had any currency whatsoever. And many of those applications were indeed fundamental applications for the mathematical foundations of programming semantics. So we, the 4 PC chairs, are really delighted that he accepted this invitation to be here and speak to us for the next hour. So thank you, Andy. He's going to tell us about Toposes of Finitely supported MSETs.
Okay, thank you. Right, so quick. So I'm not being amplified, so a quick sound check. You hear me at the back, okay? Good, okay. So if my voice drops down, just sort of shout at me or something. Yeah. So, well, I'm honored to be here. So I've been a category theorist my entire professional life, off and on. Since the 1980s, I've been applying category theory and categorical logic to computer science and the mathematical foundations of programming languages. So this is my sort of combination of conferences, and it's very nice to be able to speak at it. It's very nice to be back in Oxford. So the first time I was ever here, academically speaking, was in 1978. I know that was long before many of you were born, but there we are. And I attended something called a peripatetic seminar on sheaves and logic. So Dana Scott, who I'm sure you've heard of, was professor of logic in Oxford at the time, and he just started organizing what came to be called PUSLs, peripatetic seminars on sheaves and logic. And I went to, I can't remember which, it's a small number, less than 5. I think maybe it was the 3rd or 4th PUSL ever in Oxford in 1978. And it was a fabulous time. So there was much talk of sheaves and logic and constructive logic. Elementary topos theory was a young and very vibrant subject and very exciting to be working in. So it was all very nice. So later on, I started applying categorical logic in things to do with computer science. And so, for example, I've worked on things like the mathematics of underlying various ways of treating binding structures in programming languages. That's one thing. And I've also been more recently done some work on homotopy type theory, univalent dependent type theory, and its semantics. And in both, so toposes have always been something that I've been interested in. But in both those cases, particular sorts of toposes sort of reared their heads. They were the things that turned up as useful, and there were particular sorts of topos, finitely supported MSETs, and for different reasons maybe, or slightly unexpected that they kept on cropping up. So I thought I would take the opportunity to devote a talk to that sort of topos to tell you what the examples were that I've seen, and maybe interest you in whether you have a situation in which you could use them, or even more likely that you could probably tell me something useful about them that I don't know, which is quite useful. So, so toposes are going to be the heroes of this talk. And I'm sure many of you know some topos theory, but I think that I probably should start with a definition of what a topos is, so that we're all on the same page, as it were. So here's a very succinct definition of what an elementary topos is. It's a category with finite limits, and in which every object, the contravariant power set, sub-object functor to sets. So the functor from E op to sets, which is take the sub-objects with parameters from the object X. You want that to be representable for each X. So if I unwrap that definition for you, that's just saying that for every object X, we've got some object which we'll call the power object, P of X, And it comes along with a particular subobject of x cross px, which is going to be universal amongst subobjects of the form x cross something. So if I've got a subobject R, subobject of x cross some y, then there's going to be a unique characteristic morphism from y into the power object, such that when you cross with the identity and pull back the universal relation, you get exactly R. So it's a very simple definition, right? But not so easy to satisfy. So the cool thing about it is it's easy to state, but it has lots of consequences, which just from the definition are not at all obvious. It's a way of characterizing category theoretically what power sets are, and that can be a very powerful thing. So simple to state, hard to satisfy. I mean, I'm lying slightly because just having finite limits and power objects is all very well, but you probably want to have at least some axiom of infinity around. So you better want to have, say, a natural number object in the category. And actually, for many applications, especially the ones to do with dependent type theory, you probably want to have a lot more than that, namely some notion of universe objects in the category. So there's a literature on that kind of thing, but I would say that universe is probably a topic where we're still learning about what exactly we should say about what is the right category theoretic notion of a universe, a topos within a topos, as it were. And evidence of that, for example, I point you at this very interesting paper of Daniel Gratzer, Mike Schulman, and John Sterling from a couple of years ago. So that's so-called strict universes. So there's a thing called realignment that came up in the modeling of univalent universes in homotopy type theory, which turns out to be both very useful and useful elsewhere. I think John uses it in his work on using arting gluing to prove meta-theoretic properties of programming languages. So there's more to say about universes, but I'm not going to say anything more about them in this talk. Okay, so those are what toposes are in general. So the subject of this talk is a particular family of toposes, categories with finite limits and power objects. And they're all ones based around having a monoid around and looking at M sets. But before I tell you about them, let me say that, I mean, that definition that I gave you, succinct though it is, it's not the only way of saying what a topos is. So it's answer number 2 in André Joyal's list of 7 answers to the question, what is a topos, that Peter Johnston mentions in the introduction to his magnum opus on a compendium of topos theory. And the reason there are so many objects is why Peter called those books Sketches of an Elephant, or The Elephant, as people just tend to call it, referring to that parable about the 4 blind Indian men who were shown an elephant and asked to describe what it was, and they all touched different bits of it and said different things. And the fact is that toposes have, well, they have a distinctly logical aspect, but they also have a geometric aspect, right? So, I mean, from a logical point of view, toposes correspond to theories in a certain kind of extensional intuitionistic higher order logic, and there are strong connections with intuitionistic set theory and also with dependent type theory as well. And I mean, you know, when you say to somebody, you've got some particular category, you don't say what the objects are, who cares? It's the morphisms which are an important thing in a category, right? Morphisms, when you're talking about logical aspects, would be the functors that preserve that structure, finite limits and power objects, and maybe the natural number object as well. So the so-called logical functors. And that's quite different from the kind of morphisms you would use from the geometric side. So, I mean, when Grothendieck originally formulated the notion of what's come to be known as Grothendieck topos now, he was thinking of them as generalizing the notion of topological space via the category of set-valued sheaves on the space. And from that point of view, the right notion of morphism is a so-called geometric morphism. So that's a functor that has a left exact, left adjoint. And both the logical and the geometric aspects of toposes get kind of intertwined, and react with each other in interesting ways. And we'll see a little bit of that in this talk, though not very much, actually. Yeah, so I'm going to be talking about a particular kind of toposes. Oops, sorry. So these will be very simple. They're the ones associated to a monoid. So let's suppose I have a monoid M. I'll use multiplicative notation. So I'll just write the monoid operation. So it's a binary operation. It's associative and has a unit element. I'll just write juxtaposition for the operation. I'll write the number 1 for the unit. So an M set, right, as I'm sure you know, and I'll use left actions rather than right actions. So an M set is a set equipped with a function of this kind. So you take a monoid element and an element of the set, and you get back another element of the set. And we just want this associativity and unitary properties to hold. And the morphisms of M sets are just functions that commute with the monoid action. Compositions and identities, as in the category of sets. Okay, so that's just an instance of a presheaf category, right? So a monoid is a one object category, and so M sets to the M is just sets to the C op when C is a one element category. So we know lots about that. I mean, it is a topos, right? So let me just sort of tell you what the finite limits and the power objects are. Finite limits, very simple. They're just created by the forgetful functor to the category of sets. So that's dead easy. Power objects a little bit more involved, right? So the power object of an M set, it's not the set theoretic power object. It's subsets of M cross X, but not all subsets, but the ones which are stable under the monoid action. I'm going to use this notation on this slide. So I'll read this as M forces X to be in S. So S here is just some subset of M cross X, just a set of pairs, monoid element and element of X. But instead of writing pair MX is in S, I'll suggestively write that M forces X to be an element of S. So the stability property we want is if M forces X to be in S, then if you multiply M by M prime and you act by M prime on X, then you want to remain in S. Okay, so it's actually S is a sub-object of M cross X once you make M into an M set through left action. And that turns out to be the elements of the power object. I mean, what's the action of the monoid on such subsets, right? So if I've got a monoid element M and such a stable subset, I can get another one, M dot S, and that's given by this formula here. So M prime would force X to be in this M acting on S just when M prime times M forces X to be in S. So it's simple enough, you know, completely concrete kind of thing, but it's a little bit more than just taking power sets. It's not, as it were, you don't get the power object just by going to underlying sets and taking power objects. You've got this M cross stuff going on. Now, why is that a topos? Well, you know, I mean, you have some checking to do, right? I told you what the power object was, right? What's the generic, what's the universal relation, the membership relation. So it's a sub-object of X cross P of X, and it's just those pairs X and capital S where the unit element forces X to be an S. So you just look at what's happening at the unit element. So that's that turns out to be a sub-object of X cross PX, and it's generic, it's universal amongst sub-objects of X cross something. But I'll leave you to do the calculation for why that works out. Okay, now we're going to be looking not at arbitrary abstract monoids, but actually concrete ones that come presented as a set of functions on some set. Okay, so let's fix some arbitrary set A and look at the monoid of all possible endo functions. So that's sometimes called the full transformation monoid, T sub A. So the elements of the monoid are functions from A to A. The monoid operation is composition. The unit element is the identity function. Okay, and let's suppose that we have a monoid which is presented as a submonoid of that. So M is some set of functions from A to A. closed under composition and containing the identity function. Okay. So if I've got that information, then I can talk about M sets which have a finite support property. So this is the, you know, in this talk, the key definition. What does finite support mean in this particular context? I mean, it might mean something else to you in other contexts, but in this context, this is what I mean. Okay, so I would say that an element of an M set is supported by some particular subset of A. Think of A as atoms or names or whatever. So I've got some set of atoms, and that's going to support X if we've got the property that for any pair of things in the monoid of functions, when the two functions agree on S, then they have to act the same on X. Okay, so if that's true of S, then S is a support for little x. So if S has a property that any pair of functions in the monoid act the same on S, then that necessarily means they act the same on X. Then we'd say that S supports X. Okay. So you think about it, I mean, you could make A itself into an M set just by acting by function application. And from that point of view, an element of A is actually supported just by singleton A. That's pretty straightforward. And supports work nicely with Cartesian products, so that, I mean, for example, if I have a little x in capital X and an x prime in capital X prime to M sets, X and X prime, and if little x is supported by S and little x prime by S prime, then the union of those two sets will be a support for the pair X prime in the product M set X cross X prime, which is just given by Cartesian product with the monoid acting in each component separately. So support is quite simple in some cases. For the power object, there's not much I can tell you in general. So I mean, what's a finitely supported element of the power object? In general, you can't really say much more than just apply the definition. So in some cases, you can explain it a bit more easily, but in general, it's quite a complicated notion. Okay. So a topos of finitely supported M sets is just simply, it's the full subcategory of the topos of M sets, where you look at the objects with the property that every element in the M set is finitely supported. Okay, so for every little x, there is some finite set of A which supports that little x. So we cut down to those objects, the ones where all their elements are finitely supported. And that's what this category is. It's the full subcategory of M sets containing those objects. So that's a topos, right? Now, why? Well, let's just do a little bit of topos theory. Not very hard topos theory, but oh yeah, I should say also, I mean, maybe the notation is not great, right? Because this is not really, you don't start with an arbitrary monoid and form sets to the M sub Fs. I mean, you need to know that M is presented as a submonoid of some full transformation monoid TA. Okay, so maybe that would have been a better notation, but I'm not going to do it. Now, of course, I mean, Cayley's theorem works for monoids just the same way it works for groups, right? So, I mean, every monoid is a submonoid of a full transformation monoid. You could take A to be M itself, right, and represent monoid elements as functions from M to M through just by multiplying. But it might be that the notion of finite support you get for that representation of M as a set of functions might not be the one that you want. I mean, so often monoids come along as particular collections of actual functions on some particular set of interest. So it's, you know, the notion of finite support a priori won't necessarily be the same in this case as in the one that you start with. Anyway, I'm just going to use this notation. I won't use this notation. Why is it a topos? Well, what have we got, right? I mean, it's a full subcategory of this pre-sheaf topos. It's not hard to see that the inclusion creates finite limits. So you calculate the finite limit of a diagram of finitely supported M sets just by calculating the finite limit as a set, and that has a unique action on it, and then that will everything will be finite supported if it's a finite diagram that you're taking the limit of. And the inclusion reflects isomorphisms. That's pretty straightforward to see. And the inclusion has a right adjoint, right? And that's just given by the operation which an object would take an M set and just restrict to the subset of those elements which are finitely supported, right? So I can cut down from all the elements of an M set to the ones that have the finite support property, and that's the object part of a co-reflection, a right adjoint from M sets into finitely supported M sets. And I think I forgot on that slide to say that right adjoint also preserves finite limits. Quite important. Okay, so we can just apply one of the monadicity theorems, but in this case for a comonad, right? So this category is equivalent to the category of coalgebras for the comonad induced by this reflection. So I didn't say the right adjoint does preserve finite limits. So it's a left exact comonad. Okay, and there's an old theorem of Lauvier and Tierney that says that the coalgebras for a left exact comonad on an elementary topos gives you another elementary topos. In fact, that's kind of the typical way of geometrically getting a quotient space from a space. So these finitely supported M sets, it's sort of like it's geometrically speaking a quotient of M sets. There's a geometric surjection from M sets to finitely supported M sets. Yeah. So finite limits as in M sets, and the power object in this topos is just got by applying the right adjoint to the power object in M sets. So you form your power object in M sets and then cut down to the things that happen to be finitely supported, and that will act as a power object in this topos. So these are the toposes I'm interested in. Well, I wasn't interested in them, it's just that they thrust themselves at me in certain circumstances so that you couldn't really ignore them. And I just want to tell you 2 or 3 examples that cropped up, right? So the first one will be to do with the mathematics of syntax involving binders, about which I'm not going to say anything. I'm just going to tell you what the topos was that was involved with that. And it's a particularly special case because the monoid that we'll look at actually is going to be the group of invertible elements of the full transformation monoid. In other words, the symmetric group on countably many things. So A will be just some countably infinite set, let's say for concreteness, the actual natural numbers, and we're looking at all possible permutations of the natural numbers. So that's a group, but it's a subgroup of the you know, it's a group of functions, as it were. It's a subgroup of the full transformation monoid. So we can look at finitely supported G sets, M sets for this group Sn, and that's the topos that Jamie Gabay and I used when we were doing our work on nominal sets. So we called it the topos of nominal sets. But we knew from the start that it was equivalent to a particular sheaf topos. So if you take finite sets and injections and you put the so-called atomic Grothendieck topology on it and look at sheaves for that, you get something called Shanwell's atomic topos. And that has been known for decades and known to be the classifier in the sense of geometric theories of the geometric theory of an infinite decidable set. But what was nice about this way of doing things, as opposed to doing it in terms of sheaf theory, is that because you've got a group, the power object is a bit simpler, right? So instead of having subsets of M cross X as the elements of the power set, because the monoid is a group in this case, it's enough just to look at what happens at the unit element. So you can actually look at subsets of X rather than subsets of G cross X. Not all of them, but the ones that are finitely supported. But that just makes calculations a little bit nicer looking. And in particular, it means that we're in a topos which is Boolean. the logic is classical. The law of excluded middle is satisfied. Axiom of choice is not satisfied, but the law of excluded middle is satisfied. So the topos of nominal sets is a nice place in which to do calculations. And it turns out to have a very rich and interesting theory of things like freshness of names and binding names in the sense of statically scoped binders, and doing recursion and induction modulo alpha equivalents of bound names and so on. So none of which I'm going to talk to you about, but there's a book you can read if you're interested in. And actually, nicely, this also turns out to be an instance of one instance of the scenario in which you look at data where you've got some notion of symmetry, and you cut down to the data which is finite modulo the symmetry. So this is what Mikołaj Bahanchik rather sort of tongue-in-cheek calls slightly infinite sets. So the sets where they may be infinite, but there are only finitely many orbits for the group action that you've got on them. And these nominal sets are just but one instance of notions of symmetry that work really nicely to have a rich and interesting theory of orbit finite data and automata on them and algorithmics of various kinds for that. And again, there's an online book that I recommend you can read about that kind of stuff. So the Atom book from a few years ago. So that was my first introduction to finitely supported M sets. But I want to, instead of telling you more about those things where we're talking about the symmetric group on the natural numbers, I want to talk just about something which is closely related, but not maybe quite as well known. Quite nice to do this because one of the references is Sam Staton's PhD thesis. Hello, Sam, wherever you are. And what a fine PhD thesis it was. One of the things that Sam was doing there, so he was looking at, for various reasons, at a sort of semantic foundations for not name permutation, but name for name substitution. And he used an analog of the Shanuel topos where you take finite sets and all functions rather than finite sets and injections and put a certain chief topology on it. And so he was using a certain chief subcategory of pre-sheaves on finite sets and functions. A bit later on, a year or so later, Jamie Gabay and the late lamented Martin Hoffman wrote an interesting paper about so-called nominal renaming sets. So they were looking at renaming in the context of sort of nominal sets. And they actually explicitly used a topos of finitely supported M sets. For them, M was the finite functions from numbers to numbers. So those functions from numbers to numbers that are only the non-identity on finitely many different things. And they develop an interesting theory of properties of renaming within that kind of topos. And then more recently, just a couple of years ago, Andrei Popescu had a nice paper in IJCAR about so-called renaming sets, or Ren sets as he called them, and theories of recursion based on them. And he has so these two toposes are about simultaneous renaming, where you might rename A, B, and C to be A, D, and X or something simultaneously. Andrei axiomatized this single name for name renaming. So a renaming set for him, it's a set equipped with a ternary operation. So you should think of this as, like here, where are we? Rename A to be C. So A and C are elements of N in this thing X. So we're assuming X is some set that has a notion of single renaming on it. What is that notion? Well, it's just an operation that satisfies these equations. Wow. I mean, those are all equations that renaming satisfy. Why are those the right equations? Are they enough, as it were? And it turns out there's a kind of nice mathematical answer to why they are enough. See, I mean, here, for example, if you think of what are the finite finite renaming functions that are generated by single renamings, they're all going to be non-injective, right? Because they will all map infinitely many things to you know, yeah, that you don't through composition get anything like all the possible finite functions from nice numbers. I mean, how do you get swapping, for example? But on finitely supported things, you do, because if I want to swap A and B rather than just renaming A to B, I can choose a third thing, C, that's not in the support of the X that I'm interested in, and send A to C and then C to B and B to A, you know, kind of thing you would do if you wanted to implement a swapping, but you just had assignment around to do it with. So on the finitely supported things, then this turns out to be a little bit more general than you might have thought, and actually completely general in the sense that you can prove, I did prove a theorem that all these three categories they're all equivalent to each other, and they're all equivalent just to the topos of finitely supported T of n sets. You take all possible functions from numbers to numbers as the monoid, and look at the finitely supported M sets for that monoid. And that category is equivalent to Sam's one, to Jamie and Martin's one. Maybe not so surprisingly, but you still need to work it a little bit. But it is also equivalent to Andre's Ren sets. And that's a little bit more difficult because you need, well, you need to see that this kind of thing is presenting enough of you know, to get all the finite functions. So there are classical results in semigroups about transformation semigroups on finite sets and equational presentations of them, and using this work that goes back, I think, to the 60s, I guess, probably. And so one can leverage that to as part of the proof of this theorem. So that's quite nice. There's a kind of unification of all these things are talking about up to equivalence, the same thing. Let me turn now. Just one more before I turn to the next class of examples. So there's an interesting relationship between this topos and nominal sets. You have the symmetric group is a submonoid of the full transformation thing. So that inclusion is going to induce a geometric morphism from this topos of finitely supported sets back down to the Chaniol topos, to nominal sets. And that relative topos is probably a great place in which to do both kind of permutation and renaming stuff with respect to properties of syntax with binding. But it needs a more investigation to justify that. In particular, I don't know what the internal modal type theory of this relative topos is. I don't even really know what I mean by that. But I know people who do know what I mean by that. Daniel Gratzer, I think, probably would know what I meant by that, even if I don't know what I meant by that. Right? So modal type theory is an emergent aspect of dependent type theory that isn't, as it were, quite in a stable state at the moment. Let me turn in the rest of the talk to the other kind of example. So these are things that arise from trying to give category theoretic models of dependent type theory where you have universes that satisfy the univalence axiom of Vygotsky. Never mind what that is. If you don't know, I'm not going to tell you, but it's a kind of extensionality principle for universes. And it turns out that especially if you want models which have computational content, people have looked at all sorts of pre-sheaf toposes arise, and you put a Quidlin model structure on the pre-sheaf topos and look at universes of fibrations within that. And if you're lucky, you'll get out a univalent universe. And what I noticed is that a lot of those pre-sheaf toposes turn out to actually be equivalent to these toposes of finitely supported M sets for various monoids M. And that might be a useful way to kind of calculate the details of, because calculating with these fibrations gets quite hairy. And some aspects of these models look a lot nicer. I'll come back to this if I've got time right at the end, in this M sets view of the world than they did in the original pre-sheaf view of the world. However, that thesis never really took off. I was planning to do much more on it, but then it kind of occurred to me and a PhD student, Ian Orton, that actually a much easier thing to do would be just to be a bit more sophisticated and work in the so-called internal type theory of the topos that you're interested in, and develop a kind of synthetic account of what the vibrations in the universes are. So that overtook this work. And so this is kind of not really been developed very much. But let me take this opportunity just to tell you what these toposes were, and maybe encourage somebody to pick the work back up again. So what kind of monoids arise here? Well, here's one. So let's start with so-called Cartesian cubical sets. So that's the comes from what Grothendieck called the smallest test category. Never mind what that is, but you're interested in getting the homotopy types of this Quillen model structure on the pre-sheaf category to actually be the same thing as homotopy types of actual topological spaces, if you care about that kind of thing, which I have to say I don't, but never mind. I care more about the type theory from a logician's point of view, but never mind. What is that category? We just take non-empty finite sets with two distinguished points and functions which are arbitrary functions that send the distinguished points to themselves. So bipointed, non-trivial finite sets and functions preserving the points. Take pre-sheaves on that, and then that turns out to have an interesting notion of vibration in it that gives rise to a model of univalence. But that is equivalent, it turns out, to finitely supported M sets, where the monoid M is dead simple. It's just numbers and you add 2 points. Let me call them 0 and 1. A bit confusing because I know 0 and 1 are numbers, but this 0 and that 1 is not the same as the 0 and 1 in there. You notice that's a disjoint union, but I just need an end point and the beginning of the interval and the end of the interval, and then countably many names basically for Cartesian axes. Okay, so that's, if you look at all endo functions, so the full transformation monoid on that set, and do finitely supported M sets for that, that's equivalent to this pre-sheaf topos. So it's gives you a way of calculating with Cartesian cubical sets using monoid actions rather than pre-sheaves. So from that point of view, it's quite nice because now a Cartesian cubical set, it's just a set that has this monoid action on it. And the monoid action is to do with substituting so the ij's and k's in N, they're like names of Cartesian indices, and you're going to substitute for them other axes, sorry, Cartesian axes. So you're going to substitute, you might substitute j for I, but you might also substitute 0 for I or 1 for I. Okay. So if we had an object that was, say, supported by I, j, and k, right, it would look like this cube. You've got an I-axis, a j-axis, and a k-axis. So if I come at that object X and I say, I'm going to substitute 1 for I, I'm going to pick out this red face of the cube. And if I say I substitute, I don't know, 0 for I and 0 for j, I'm going to pick out this line segment on the k-axis. And if I also then make k be 0 while I'm making I be 1 and j be 0, then I'd be picking out that point. So, 0 dimension, 1 dimension, 2 dimension, 3 dimensions, and so on. And if you've got a support that's got 42 different names of axes in it, you're talking about a 42-dimensional thing. But the point is that's the dimensionality of your cubical set is implicit. It's not explicit, right? Whereas with the pre-sheaves, you have to say what world you're in, and you move from world to world explicitly with functions between the worlds. And that is a little bit hellish, because believe me, the notion of vibration is already quite complicated to state. And it's even worse when you have to do it in terms of pre-sheaves. So this kind of implicit dependence that the monoid thing gives you just allows you to forget about that kind of rather nasty, so-called weakening hell, and concentrate on the important stuff. So it's quite pretty, and if I've got time, I'll mention some more about that. So it turns out this is not at all an isolated incident, right? So the first model of univalence that had computational content that the world saw wasn't this Cartesian cubical one, but it was this one where you don't take all functions on this set, but you take the ones that are injective on the things that don't map to 0 and 1. Okay, so that's a particular set of functions that are closed under composition and contain the identity. And that pre-sheaf topos is the one that these three guys used in their first model of cubical sets that was univalent. And then that turns out to be quite tricky to use if you're calculating like pi types, dependent products. Their next attempt with some other, well, is Thierry Coquin is kind of the common factor, working with various people, used a slightly more complicated monoid. So that would be where you look at the free De Morgan algebra on N. What's a De Morgan algebra? It's a distributive lattice with an involution that satisfies the De Morgan identities with respect to join and meet. Okay, so it's an algebraic theory. So take the free algebraic theory on countably many generators. And that's got much more structure in the interval. So you've got a kind of connection and you've got a reversal. So that allows you to do computations on using the interval and hence homotopies in a little nicer form. But that turns out so their Cartesian, their cubical type theory there used a particular pre-sheaf topos, which is just equivalent to finitely supported M sets for this particular monoid. So it's yet again another example. There's nothing special about cubical, it turns out. I mean, cubical things were what Dan Kahn originally used in his stuff about, sort of algebraic approach to homotopy theory, but then it slipped over into simplicial sets quite early on in the development and kind of stayed there. So most combinatorial, people doing homotopy theory from a sort of combinatorial point of view would use simplicial sets. Well, simplicial sets also are an example, which is very nice. So if you take the set A now to be the integers with a top and a bottom point added, and you take the functions to be order preserving functions that send the bottom to the bottom and the top to the top. So the minus infinity goes to minus infinity and plus infinity to plus infinity, but otherwise just order preserving on the integers. That's a monoid of functions. If you take finitely supported M sets for that, that's equivalent to the topos of simplicial sets, sets to the delta op, delta being finite ordinals and finite non-empty ordinals and order preserving functions between them. So simplicial sets fits into this picture nicely. Actually, let's go even one step further. So this is even less well known, I think. This observation is in a thesis of Eric Faber from a few years ago. We can go down not from the cubical to the simplicial, but actually to the globular, right? And so let me mention that. So what's a globular set, right? It's like a multi-dimensional graph. So you have naught cells, you have 1 cells, you have 2 cells, you have 3 cells, you have cells of any finite dimension, and you have a domain and a codomain operation. So an n+1 cell, you can take its domain, and it'll be an n cell. Take its codomain, it'll be an n cell. And those domain and codomain operations satisfy certain identities that you would guess if I told you to guess them, which are written there, the so-called globular identities. We want the reflexive globular set. So we're going to put in, I mean, what would be identity functions if we had the notion of composition, but in globular sets, this is the graph, the underlying graph of a high dimensional category, not the category itself. But we'll have insertions from naught cells into 1 cells, 1 cells into 2, 2 into 3, and so on. And so the domain and codomain of an identity are equal. So that's this identity here. So that's what a reflexive globular set is. You can see that that's just a certain, I mean, I've got a certain diagram there, right? So the category of globular sets and morphisms that preserve the structure, it's just a pre-sheaf topos, right? I mean, it's pre-sheaves on a particular category. Okay. But that pre-sheaf topos is equivalent to a category of finitely supported M sets. And actually really rather a simple one. So much simpler, I think, than this description. So the monoid is its elements are of the form, I'll call it dBn. So n is ranging over numbers, b is ranging over bits, source and target. Okay, so you should think of d naught n if we're acting on something. It's take the nth dimensional source of x, and d1n is take the nth dimensional target. Okay, let me just go back there. And what are the monoid identities? So it's a semi-group actually. I mean, because we want an identity element as well, but these are the non-identity elements. And when you multiply, it's dead simple, right? I mean, so if n is strictly smaller than n prime, then this multiplication is just the left-hand thing. And if not, then it's the right thing. So that's a monoid, okay? And if you look at M sets for that, okay, now hang on a moment, that's a monoid, but it's not obviously a monoid of functions, is it? I mean, it's not functions from on some set, it's some abstract monoid that I've just told you there. But as I mentioned, you can always regard any monoid as a monoid of functions using Cayley's theorem. So let's do that in this case, right? So that's a submonoid of all the possible functions from M to M. So M is just a countable infinite set of things, okay? So we can take the notion of finite support for that embedding. And that turns out to coincide with what you'd hope it would be, because what you'd want, right, is that you want finite dimensionality. So you want an element of a set being acted on by this monoid. You'd say it had dimension at most n if when you take, say, the source in dimension n of x, it doesn't change x. And if that's true, that would also be true of taking a target, and it would also be true for m's that were bigger or equal to n as well. Okay, so this is sort of saying that you know, x doesn't involve anything of dimension more than n. Okay, so that doesn't look like a finite support property. It looks kind of similar, right? But actually, it turns out to literally is the same thing as the finite support property once you embed M as a submonoid of this thing. So this category of finitely supported M sets for this monoid turns out to be equivalent to reflexive globular sets. This is not a new observation, actually. It's kind of implicit in a nice classic paper of Ross Street's from the 80s on the algebra-oriented simplexes. He uses this approach to omega categories as part of what he's doing in that paper. Great. So there are my examples. I think now, as an audience, you could say, well, that's all very well, but, you know, so what? And it's a good question. I mean, you know, so you've got these various finitely supported M sets equivalences of some sheaf toposes, quite a lot of pre-sheaf toposes, and so on. Is it actually useful to take that point of view? And I think it is. I mean, I wouldn't be talking about this if I didn't think that, right? I mean, but there are pluses and minuses. I mentioned one of them already. The M sets view is quite nice because you don't sort of have this kind of typical Kripke style possible worlds, which is not that bad, but it does kind of interpose itself in nasty ways. And with a monoid, you've only got one world, right? Because there's only one object. It's a one object category. Unfortunately, with a non-trivial monoid, of course, you've got lots of world morphisms because those are the elements of the monoid. So you've still got those around, and you might have to say naturality conditions with respect to those changes of the world to itself. But actually, sometimes you can even avoid that. If you use co-free functors on index families, you can sometimes even avoid saying anything about naturality. And if you've got a group rather than a monoid, then you can just look at what's happening at one and the kind of the world aspect. It goes even further away, which is what was happening with nominal sets when we did it. But I think the real plus is that in finitely supported M sets, some constructs that you might be interested in really are easier to calculate with. And that's certainly the case with these things in cubical sets where you want to develop notions of path spaces and homotopies. And let me just quickly mention that. I think I've got, yeah, just got time to do that. So if I go back to my Cartesian cubical sets, okay, which was this topos, and that's finitely supported M sets for this monoid of endo functions on this set, preserving 0 and 1. So if I call that set I, that turns out to be an interval object in the topos in a technical sense. Once you make it into an M set, right, just by acting on it by function application. And it's an object then, everything's finitely supported in it, and it has two distinguished global elements, which are going to be the begin point and the end point of the interval. And we can look at paths based on that notion of interval. And we could take paths just to be things in the exponential x to the I. So if I've got some object x, I can exponentiate with respect to I, and that will be the object of paths using I as the interval in x. And in general, in M sets, exponentials, you know, you can calculate with them, but they're not super nice because of this business of, you know, they're like with the power object, the exponential is similar. Instead of having functions from x to y, you have functions from m cross x to y, satisfying various conditions. And but in this case, I is a very, very nice special object. And actually, x to the I just turns out to look like things that we already knew about in the world of nominal sets, namely name abstractions. So they are given by pairs, where you take the dimension you're interested in abstracting over in some element of an M set. And you identify one such thing, Ix, with another such thing, simply if when you take some dimension that's not mentioned anywhere, something that's fresh for Ix, J, and K, if you rename I to be K in X and you rename J to be K in Y, if you get two things which are equal, then I'd say that that represents the same path as JY. So IX and JY would be equal as elements of the exponential x to the I. And this turns out to be a correct description of the exponential, much simpler than what it would be for x to the some other general object other than I. And I is really special. That exponentiation, that path functor, I obviously has a left adjoint, take the product with I, but I is tiny, so that functor has a right adjoint as well, which is doesn't happen very often. It kind of means that the interval is really, it's got a 0 and a 1, and it's got some stuff in it, but actually you hardly see the difference between the x's and y's at all. So it's a tiny object, and that tininess is actually super important for giving really nice descriptions of univalent universes of fibrations in this setting. And in the finitely supported M sets, you can give a completely explicit description of what the right adjoint is, and you can therefore probably calculate with it. And so to kind of get towards the end of my talk with some to-dos, I would very much like somebody, probably not me because I've kind of got hooks on other things at the moment, to really kind of take this thought seriously and do all the details of the Cartesian cubical model of homotopy type theory using finitely supported M sets for that particular monoid M, rather than using presheaves. And there will be a cool way of doing that, which is just to steal Steve Audi's very nice and extensive set of notes on Cartesian cubical sets. So he develops the whole thing up to, in a nice pedagogical way. Steve's excellent at writing stuff using presheaves. So it does get a little bit hairy, actually, and I think it would be much nicer to do it using finitely supported M sets, but I haven't done that. But somebody should do that, I think. Another thing is going back to that forcing notation. These toposes of finitely supported M sets, they definitely have interesting cumulative hierarchies of sets in them that are models of IZF, of intuitionistic Zermelo-Franknell. And Dana Scott, love him, back in the 80s, I don't know whether you can read this, but you see in February 1980 in Oxford, it says, just going over the, it says Oxford up there, right? Where we were, it's just down the road he was, right? He was producing this digitally typeset paper that was never published. I mean, it was just circulated. And it starts in typically modest Dana fashion. The whole of this discussion is just putting together of 2 + 2 from known facts in topos theory, but it's a useful exercise for me to get various things straight. Well, it's actually a useful exercise for lots of other people as well. So he develops an explicit description using a kind of forcing notation of the pre-sheaf model of IZF. And I think it would be super nice to do that in the special case where you were with these finitely supported M sets. So now you'd only have one world, you'd still have the monoid elements in the forcing position, but you do have to sort of you have to put in the finite support places judiciously in the right places. But I think that probably could work out quite nicely. So again, I don't think anybody has done that, but it's probably an interesting thing to do because I think there are probably lots of interesting, weird models of things happening in that set theory. Just like, you know, you get lots of weird, interesting, useful things like these tiny objects in these other pre-sheaf toposes. So I think that would be a good thing to do. And just to finish, I don't actually know. I mean, I don't know what these toposes are abstractly, right? So I can't say I'm talking about this class of topos, which is, you know, axiomatized in a certain way. So actually, you know, as of today, I don't know that there isn't. It could be that every growth-indic topos is a topos of finitely. So I don't think that's true, right? I'm sure it's not. But you know, until we had some characterization, so that you could then say, here's something that isn't one of them. I haven't really seriously thought about this, and I kind of suspect that somebody in this audience, I'm kind of hoping, will come up to me at the end and say, "You fool! Didn't you know that you know there is this characterization?" So it would be nice to know that. But I don't know it, but there we are. And I think that's the end of my talk. Thank you for listening. Yeah, of course, yeah.
It's close to tea time, but obviously we should have some questions, please.
Thanks, Andy, for the great talk. You mentioned at some point that you could characterize sets this way.
Yeah.
With a particular presentation.
Yeah.
I was wondering if
there's a little bit of variation there. You could do it. You don't have to use that particular set,
okay.
But yeah, yeah.
I was just wondering if you've taken that idea further and maybe taken it to quasi-categories so that you could.
Yeah.
I wonder if this idea would.
Yeah. No. So the answer is no, they haven't, but they should, right? And I told Eric, oh, this is this really cool thing. I think, you know, that simplicial sets can be done like this. And wouldn't it be nice, like, you know, because I bare my heart here and say that when I sit in talks about simplicial topology, and I have sat in a lot of talks with, and one's eyes cloud over very quickly because of all the indexing and stuff, right? It's actually, unless you're really into it, it's very hard to remember all the stuff about the simplicial identity. And this, I think, is a much easier way of calculating things, but nobody has done it, to answer your question. Yeah.
So that idea, you think, would hold some more.
Yeah, and I mean, a concrete example of that is I do know, if I just flick back to it, this way of doing reflexive globular sets, the next step, which is that you just say, well, I've got a composition structure in each dimension n with the interchange law. Well, you just say that, and it's dead simple to show that that's equivalent to strict omega categories. I mean, it would be more, sitting next to you, be more interesting, of course, to try and get at the weak structure from this point of view, and that's not so clear whether this really helps do that, but maybe it does. I don't know. Yeah.
JS. So I know that in a monoid function, it's rarely commutative.
Yeah.
I was curious to know if there's something to be said when you do look at commutative monoids.
Oh yeah. Well, I have never needed all of the ones that I've ever dealt with have been basically monoids of functions, and usually you've got a lot of functions around, so you don't get commutative ones. So I've literally, I mean, there's nothing to stop you, right, having a topos of finitely supported M sets on a commutative monoid. It's just I don't know any examples that have, as it were, arisen naturally where people would really want to do that. Yeah, so I don't know, but you know, if you ever come across one, do tell me, because I'd be, you know, like to collect them.
You first, and then one day.
Yep.
Yeah, sorry.
In this example with the monotone functions on the extended integers,
Yes.
it looked like one of these examples of monoids where you have adjoints on the left and the right. These pre-groups show up as examples of monotone functions like these, and there's a Cayley theorem for them as well.
I know absolutely nothing about that. That's interesting. So pre-groups.
Yeah, so they showed up in Lambek's work in linguistics where you can mono.
Oh, I see, where you have a joint.
So you have, it's like a group, but you have.
Yeah. Oh, I see. I can guess what it is. Yeah.
And the only like naturally occurring example is something like this, but without the
yeah, interesting. Yeah, yeah. Good. Thank you. Yeah, I didn't.
I don't know what to do with this.
No, I know. Yeah. I mean, I suppose the thing not to do, as it were, is to start with a monoid and think what to do with it. It's much better to, as it were, be in some situation where you're kind of forced to see that, oh, I can do it using that monoid. But yeah.
I think all your examples are appreciative topos.
No, the Shanuel topos and Sam's. No, Sam's topos is a. No, Sam's topos. Well, it's equivalent to a pre-sheaf topos. Yeah.
Well,
okay, but the Shanuel topos is not a pre-sheaf topos. It's a proper sheaf topos. Yeah. So they're not all pre-sheaf toposes. I know most of my examples were pre-sheaf toposes, but certainly not all of them are. No. Mind you, the kind of sheafiness that you're getting is, I mean, well, it's atomic for the Shanuel topos, and might be quite special. Yeah. Anyway, yeah.
Any last questions? Okay. Oh, yes. Okay.
Sorry, could you shout? Do I know what happens if the monoid is? Whoa. So you're with this guy down here, pre-groups. I literally no idea what that. I can kind of guess what it might be, but my straight answer is no. I have no idea. Yeah. Oh, the guess is it would be great, and it really works out, and you get a topos. Yeah. I mean, there are a lot of related concepts right around here. I mean, the Shanuel topos is like, it's continuous G sets, and you can have continuous M sets. You can have a topological monoid and take actions which are continuous. That's going to give you a topos for exactly the same reason you've got a left exact comonad sort of thing. But so the finite support thing is add example in one direction of something which probably works in other ways. Yeah. Okay. Time for tea, I think.
Thank you, Andy, and let's all thank Andy again.
Yeah.